All right. So on the second talk of the afternoon, we have Samson Zhou. Who's going to tell us what adversarially robust L0 estimation for sketches. All right. Yeah. Thanks everyone for attending, and thanks to the organizers for putting together a great week. Yeah. So this work is with Elena Gribelyuk and Huacheng Yu at Princeton, and Honghao Lin and Woodruff at Princeton. Okay, so let's start with a slide that you guys have already seen multiple times, just Moses' talk. We'll have, in the streaming model, which is going to be the focus of our talk, we'll have elements of an underlying data set S that are sequentially. And we like to evaluate or approximate some given function using space sublinear in the size M of the input S. All right, so there are lots of problems that we can consider in the streaming setting. I think this is just a subset of works that people at this workshop have considered. But for this talk, we'll focus on distinct elements. So our stream is actually going to be a set S of M elements from some universe N, integers from 1 through N. And Fi is going to be the frequency of element I, which is just how often it appears. So our goal is to find the F0 or estimate the F0 of the frequency moment of the vector, which is just the number of items, distinct items that appear throughout the stream. So let's practice. We have this stream on the left, and I guess it was a little fast, but induces the vector at the bottom right. And there are 4 distinct elements from the universe of size 5. And this is insertion only, which means that each time an element arrives, it can never be decreased. Okay, so it's known for insertion only algorithms for distinct element estimation. Well, there's a lot known, but the main takeaway is that we only need space logarithmic in the size of the universe. So there are various settings where the initial results only got constant factor approximation and 1 plus epsilon. But the point is, for epsilon being some kind of constant, none of these use polynomial space in N. Okay, so here's a taste of how these algorithms generally perform. It's not the most optimal one, but it gives intuition that will be instructive for later purposes. Okay, so the algorithm, one algorithm is that you can sample elements of the universe N at some rate 1/2 to the I into a set Si. Okay, so for S0, you just look at all the elements in the universe. For S1, you look at maybe half the elements in the universe, so on and so forth. And you're going to pick the set Si with roughly 1/epsilon² log n items in the stream. So this is quite, not quite a sublinear space algorithm, but you can implement this in a way so that if you have more than 1/epsilon² log n items, you can just discard the set and move on to the next level. And at the end of the stream, you have the set Si that has a certain number of items in the stream, and you're going to output the number of items in Si times 2 to the I, which is the inverse of the sampling probability, to get a constant factor approximation to the number of distinct elements in the stream. Yeah, so that is a vanilla streaming model. And the case we'll be looking at today is for an adversarially robust stream. So in this case, the elements of the underlying data set arrive sequentially, but also adversarially. And our goal is still to do something interesting in space sublinear the size of the stream and the universe. Okay, so we have this stream, the same stream from before. Let's say the adversary feeds a 1. We are trying to count the number of distinct elements. We see 1 distinct element, we output 1. Then the adversary gets to output the next input to our algorithm. So they choose 4. We've seen 2 distinct elements. The adversary chooses another thing, so on and so forth. And at some point, the adversary might make us mess up, and then our algorithm has failed. Okay. So yeah, this model handles adversarial robustness, but I think one application that adversarial robustness is used that's often overstated is it also helps in adaptive settings, where somehow the output of your algorithm at a previous time is then fed into your algorithm in the next time. Okay, so it's known for adversarial robustness for insertion-only streams. There's this nice work by Omri and co-authors that initializes the problem and gets 1 over epsilon cubed times polylog n. There's a follow-up work beautiful work that uses differential privacy for adversarial robustness. They use differential privacy to hide the internal randomness of these algorithms. And they get 1 over epsilon to the 2.5, but still polylog n. And finally, we show that, well, there's almost no loss in either the epsilon factors or the log n factors. Okay. So the point is, for adversarial robustness for insertion-only streams, we have nearly tight results saying that you essentially don't need to pay anything for adversarial robustness. Okay, so for insertion deletion streams, the story is quite different. So what is an insertion deletion stream? Well, we have each update can either increase or decrease a coordinate of the underlying frequency vector. So let's say the teeth update will change the a teeth coordinate, which is something between 1 through n, by delta t. And for simplicity, let's assume that delta t is like -1 or 1. So each update either increases or decreases the coordinate. Okay, so the only thing that is known for insertion deletion streams is another work by Omri and Christoph and Talia that says, well, we can get a constant factor approximation in space m to the 1/3, where m is the length of the stream. In particular, there's nothing known for constant factor approximation in space polynomial in n. Okay, so you might ask, well, what are general approaches for insertion deletion streams? So one general approach is a linear sketch, where an algorithm will maintain a vector ax for a matrix A throughout the stream, right? So the updates of the stream are updating x, and you just keep ax at all times. And afterwards, you output f of ax for some post-processing function f. So this is a linear sketch, and it turns out that the algorithm I described earlier can be implemented as a linear sketch. More importantly, there's been some previous work that says, well, for sufficiently long streams, all insertion deletion string algorithms can essentially be viewed as a linear sketch. Okay, so there are lots of caveats here. In particular, the stream has to be like exponentially long, but under some conditions, you might as well just consider linear sketches instead of general insertion deletion streaming algorithms. Okay, so that is a way to simplify approaches for insertion deletion streams. But there's some bad news, which says that, well, for linear sketches, they're generally not robust to adversarial attacks. In particular, this work by Hart and Woodruff showed that for LP estimation, where you want to estimate the p norm of a vector that arrives in a stream, you essentially need linear space. And their attack works by learning the sketch matrix. So I'm not going to go into this too much, but they iteratively find rows of the matrix in A by acquiring Gaussians. And once they find vectors that are weakly correlated with A, they look at the subspaces that are orthogonal to these rows and continue the attack. But the point is that the attack randomly generates Gaussian vectors, and the analysis crucially uses the rotational invariance of Gaussians. So these are both not going to be applicable for us because, one, if we have Gaussian vectors, this is infinite precision, which is not quite realistic for data streams. And two, the rotational invariance of Gaussians means that we can just look at the directions, like the magnitude of the resulting vector after we hit the vector with the sketch. And this is inherent to L2 estimation, which is not good for distinct elements. In particular, this attack does not apply to L0 estimation. Yeah, so our main result is saying that, well, there is an attack on linear sketches insertion deletion streams. In particular, there exists some constant C such that if you want a C approximation to the number of distinct elements, then you're going to need a polynomial amount of space, polynomial n. It's a small polynomial, not a large polynomial, so like n to the 1/3, not the n squared. In particular, if you want a constant factor approximation to the number of distinct elements for a sketch of size R, you can do this using roughly R to the 8 queries. Yeah, sorry.
any type of assumptions you can make triply exponential line whatever streams that says linear schedules are also the only thing you can do for adversarially robust?
Yeah, that's a fantastic question. We thought about this a lot. We didn't see one because the main issue with adversarial robustness is that it's an interactive procedure. So after each step, you need to answer the query correctly. And that inherently means that you need correctness over like a doubly exponential stream. And then the space results become kind of trivial because if you just union bound, then yeah, the space becomes too large just from the failure probability. So that's a great question. It'll be something that I would really like to find the answer to.
Do you have a guess if that's even true?
I don't know because I guess like they're all pseudo-heuristic algorithms. So yeah, I don't know. Okay, so any other questions? All right, so yeah, then if there are no further questions, I'll start talking about the actual attack. Okay, before I do that, I just want to mention a specific parameterization of the problem. So we'll be talking about the gap L0 norm problem. So here, alpha and beta are constants, fixed constants, alpha is less than beta. And we want to distinguish the case where the number of distinct elements is less than alpha n or more than beta n. In particular, if you have some good enough constant factor approximation, then it can solve this problem. So we're going to attack this problem, which is perhaps an easier problem. In particular, if neither of these cases hold, then the algorithm is allowed to output arbitrarily. Okay. All right. So intuitively, a sketch matrix A can preserve a large amount of information about a small number of coordinates, or a small amount of information about a large number of coordinates. Yeah. So I'll give some examples. One example is that there can be a row of A that is non-zero in only a single column. More examples in the next slide. For example, the matrix that we talked about before in the insertion-only algorithm samples a random set of coordinates that have large information revealed about them. But there can also be coordinates that only appear in columns with a large number of non-zero entries. So let's look at this matrix. So here, A is a sketch matrix. This is the frequency vector. And so if you take the matrix vector product, you have to believe me that the resulting vector that is stored in memory is just this vector. Yeah, so this is what the algorithm has access to at the end of the stream. Now the point is that this matrix has two rows. The first row is exactly what I said earlier. It's one sparse row that reveals a lot of information about this one coordinate. Okay. So this is the non-zero coordinate. It reveals that this is a 1. On the other hand, we can have a really dense vector right here. And then it reveals less information. For example, if we take the dot product of this row with the actual frequency vector, it's 0. And so we actually don't ever learn that this coordinate here is non-zero. So these are kind of two cases. One can have a sparse vector, one can have a dense vector. And so a general scheme for the adversary is that it wants to gradually learn the sketching matrix. So our strategy is going to be similar to the one by Hart and Woodruff at a high level. We're going to try to iteratively identify the significant coordinates and then set them to be 0 in all the future queries. So basically, the sparse parts of the matrix won't tell us anything. And then after we learn such coordinates, the query has to rely on the dense part of the matrix, which in this example before also doesn't tell us very much. So that's going to be the main outline of the attack. Okay, so let's consider a very extreme example where the sketch AX is just a subset S of R coordinates of the frequency vector. Okay. So we're just sampling R coordinates into a set S and looking at whether there's non-zero in the stream. So the attack is really simple. We just want to identify S and then put zeros on S and ones everywhere else, and the sketch will think it's going to be 0. The number of distinct elements is 0. Okay. So to do this, we're going to borrow some technology from adaptive data analysis. In particular, we're going to discuss the, let me introduce the interactive fingerprinting code problem. So in this problem, an algorithm P will select a set S of coordinates unknown to the fingerprinting code F. And the goal of the fingerprinting code is to identify the selected set by making adaptive queries. So each of the query will be a binary vector of length n. And the algorithm has to answer consistently with some coordinate in the query vector. But the algorithm can only observe the coordinates of the query in the set. And what that basically means is that the only thing the algorithm needs to do is just to distinguish between the case where restricted to the coordinates in the set, every entry is 0 or every entry is 1. So I claim that there is a fingerprinting code, there is a sequence of queries that will interact with this algorithm P and eventually be able to detect S, identify S explicitly. Okay. In particular, there exists an interactive fingerprinting code with length n squared. Now, the gap L0 norm problem needs to distinguish between the cases where the number of non-zeros is alpha n, less than alpha n, or more than beta n. And this is actually a stronger guarantee than what we require or what we demand from the algorithm in the fingerprinting code. In this case, the algorithm just needs to distinguish between the case where everything in its restriction is all zeros or all ones. But here we need to distinguish between the case where it's the gap is a bit smaller. So this is a stronger requirement than fingerprinting codes. And so any algorithm that behaves as a fingerprinting code would also need to behave similarly to solve the gap L0 norm problem. Okay. So this means that if our algorithm is just a subset S of n coordinates, then we can use a fingerprinting code to identify the set and make an attack. Okay. All right, so that is for the sparse part. For the dense part, I want to talk about an attack on it. But before we do that, we have to actually formalize what it means to be significant. So I said that there are a number of coordinates that has significant information. Sorry, significant coordinates that have a large amount of information, and that needs to be formalized. So what we said before is that if we have an elementary vector EI that is a row of A, then we can definitely recover information about whether the coordinate I is 0 or not. So that is clearly one definition of significant that we need. Here's a worse example. So before I said that dense rows won't give you any information, but that's not quite true. Like we can look at this dense row right here, take the dot product of this row with the frequency vector, and this thing is going to be 1000, which means that the entry corresponding to the large entry in the dense row is probably not 0. So all this is saying is that, well, you can still get a significant amount of information from your dense rows. And so this is happening because the algorithm has the vector AX, and it can recover like y transpose times x for any vector y. And so if there's a y such that the ith coordinate of the product is large, you can still recover a large amount of information. So again, what's happening here is just that the ith coordinate of this thing is large, and so recovering a lot of information. So somehow we also need to account for the fact that individual coordinates can't be large after multiplying by some vector y. Okay, so that's another example of why a dense row does not work. Here's one last example. So before we had all these entries being small and one problematic entry being large. And now it's the opposite. We actually have a large number of entries being large and one single entry being small. And I claim this is still a problem. Why? Because if we take the dot product of this row with the frequency vector, it looks like 103. But since we're dealing with integer precisions, we can take this mod 10, and we still realize that this nth entry is going to be equal to the entry n, xn, is going to be equal to, 3 times xn is going to be equal to 3. So we just know that this entry is 1 mod 10. So it's yet another example of how a dense row can still give us non-trivial information about the overall frequency vector. And what's really happening here is that the fractional part of this dot product is going to reveal a lot of information. Okay. So before we said that we want to remove the coordinates that are somewhat large compared to the overall vector. And now we're saying that we still want to remove the fractional coordinates that are large compared to the overall fractional vectors. So this is the last condition. And it turns out that these 3 conditions are actually enough. So we'll have some argument that says, well, if any dense row satisfies these 3 conditions, then it's going to be indistinguishable for a certain set of inputs that we require to the vector. Okay, so now that we've quantified what it means to be significant, what we do is we pre-process the matrix. So the algorithm has access to a linear sketch AX, and we say we're actually going to transform A into a larger matrix A prime that separates the significant coordinates. And this will only give the algorithm more information. So here we have the matrix A, and we're just going to split this row into 2 rows. So this row, this 999, is now dropped down here. So we get 2 rows from this 1 row. And now this row is no longer, sorry, this coordinate is significant, but this row here is not inducing significance on any other coordinates. And also, we've only added 1 more row. Okay, so the algorithm will only have more information from A prime x than AX.
Okay. Why doesn't 999 becomes 2 rows?
This is pre-processing, so we're splitting this row into 2 rows.
Right.
And I'm saying that I can use the output of A prime x to actually recover AX.
Because some wraparound is happening?
No, so this would be a vector of length 3. So if I multiply the 3rd entry of this vector by 989, and the 2nd entry we just get the x.
So do you need some bound on the entries of A to get like so this doesn't happen really often? Or?
Yeah. Okay, so we eventually show that there's a certain number of rows that are added to A because the entries are not too large and the stream like this also not too large.
So what bound do you assume on the size of the stream, I guess? Or
the size of the stream is poly n, and we're assuming that the entries are poly n. Okay. Okay, so the resulting matrix A prime is a combination of a sparse matrix S and a dense matrix D. And in particular, the sparse matrix will have at most 1 non-zero per column. So we can use the fingerprinting tag on this. And the dense part will have no significant columns. Like here asked. We do need to show that after we break apart 2 rows, this process needs to terminate eventually. So we show that there's only rs log n rows that are added to A in this process. That's an information card. So now if there are no dense part, we can just use the fingerprinting tag. So here's the summary so far. We're just going to pre-process the matrix A into matrix A prime that is a sparse part and dense part. We're going to attack the sparse part S using fingerprinting code, and we're going to attack the dense part somehow. Yeah, so the dense part is the most technical part of the talk, so maybe this is a good time and stop and ask questions. Okay. Yeah, so if there are no questions, maybe I have like 5 minutes or so, so I'll kind of rush through this. So we'll design a family of distributions D such that we can parameterize this family with some P between A and B. And the point is that the number of non-zeros in this vector X after we generate each entry from dP in expectation will be Pn if we generate from dP and Qn if we generate from dQ. So what we're going to do is we're going to pick either a P or Q. And in these two cases, the L0 norm of the resulting vector will be different in expectation. There's going to be a constant factor separation. But we want it so that the total variation distance of the image of the matrix after hitting these vectors is small. Okay, so if the dense part looks the same for both of these vectors, then we have to look at the sparse part. The algorithm is forced to look at the sparse part, and then we can use the fingerprinting attack. Okay. So yeah, how we're going to attack the dense part is just this family of distributions D. Okay, so yeah, maybe this is getting into the weeds, so I can go through this quickly. If you're interested in the details, talk to me afterwards. But the point is that we want to construct this distribution. And how we get motivation for constructing this distribution is that we look at the total variation distance between these two distributions, P and Q. We haven't defined them yet, but we're just looking at how the TVD would look. Use some Fourier analysis to relate the distance at one point, the support at one point, to the Fourier coefficients. And then when we look at the actual Fourier coefficients, we have for a symmetric distribution, we can view it as basically the sum of a number of moments. Okay, so we can decompose the Fourier coefficient into like the 2kth moment times some decaying term. Okay. All right, so all we know so far is that the total variation distance looks like a difference between the 2kth moment between the distribution of P and the distribution of Q, the 2kth moments of these distributions, times some decaying term. So a natural question a natural goal would be to set like the moments of these distributions to be equal for the first 2k terms. So our goal now is to find the same family of distributions, but we want the first 2k moments of the distributions to match. And this is for any P and Q in this family. It's not really clear whether these distributions exist, but looking at some literatures from polynomials, they do. And so, yeah, the final ingredient is just the moment matching argument to say that, well, based on the existence of these polynomials, we can construct these distributions so that they match on the 2k, on the 2k moments for like all k sufficiently small. Great. And, yeah, so that gives it back. Yeah, so sorry the last part was a little fast, but in summary, we show that there exists some constant such that any linear sketch that provides a constant factor approximation needs like r to the n to the 1/3 rows ish. And if you actually have r rows, then this can be broken in like r to the 8th parts. Just show similar results for finite fields and real valued sketches. In particular, this result right here is the analog of Hart-Woodruff for L0 estimation. Okay, so I'll conclude with some future directions. Let's just get the low-hanging fruit out of the way first. So we can have a smaller number of queries instead of like r to the 8. Adaptive data analysis usually has a quadratic dependency. So can we get like an r² query attack? And attack against the pseudo-deterministic algorithms would also be interesting. Okay, for the higher order bits, I think this question has been asked at this workshop multiple times, whether there exists a streaming algorithm for LP estimation, not one based on linear sketches. But I think to do that first, I think we need to go to these two directions, which is what Separate was asking, whether there's something we can do for linear sketches versus streaming algorithms for adversarially robust instruction condition streams. Okay, that's not happening. Thanks.
So before the coffee break, we might have time for one quick question. otherwise, I'm sure it's gonna be at the coffee break, so you can just pester him during the break. And yeah, let's thank again Samson and Moses. Yeah, so the next talk is at 4. And after that, there will be the process session. And